of the field produced by this charge and the field produced by this charge. And indeed in the summer I'll ask you to calculate the field at a couple of high symmetry points again, so that it's a quick calculation that just shows the principles of what we're doing. You know, high symmetry point like this one, or somewhere out along this axis here, or somewhere out along this axis here. And you can see the equipotentials are these dotted lines, and the solid lines are the electric field lines. And this is a real field of a plus and a minus charge. And indeed, it's called an electric dipole field. And we'll use it to interpret some of the properties of matter when we look inside materials in the summer term. Now, the idea of a conductor, if you have a conductor, the idea is, well, because there's a force on anything that's got a charge, if there's an electric field, because inside a conductor the electrons are free to move around, they move until they cancel out all the electric fields. So in other words, a whole block of a conductor becomes an equipotential. It couldn't, because if there were any electric fields left, the electrons would move to cancel it out. They're free to move. That's what makes the material a conductor in the first place. So in the surface of a conductor must be an equipotential surface. And what people do is they say, let's say the real problem is that I've got a positive point charge next to a conductor. There's my conductor. Well, because this is an equipotential, we can the real problem is that I've got a slab of metal and a single point charge, but it's because you know, you'll see in the summer the properties of materials are extremely difficult to calculate. You replace the problem by an equivalent problem where you say, well, because this conductor here has got this equipotential surface here, I can replace the tricky problem where I don't really know where all the electrons have gone here by the simpler problem of pretending that there is a single negative charge, which is the image of this charge, as if this was a mirror here in the surface. And it's called the method of images. So if you like, it's easy to solve the electrostatic problem of a single plus and a single minus. It's really difficult to solve the problem of a single plus next to a slab of metal in which all sorts of complicated stuff is going on. But I know that in this region outside, I'm going to get the same pattern of electric field lines. And you can see as they enter in, all the electric field lines are perpendicular to the surface of the metal. So this image charge is a pure fiction. It's not there, but it enables you to correctly calculate all the field lines outside a conductor. So Christian just asked me, that's a preview of some stuff we're doing in the summer term. It's not connected with the course at the moment. But anyway, so let's do something that is connected with the course. And we got as far as the Ampere-Maxwell law. I'll write it on this side so that we've got the, I can refer to it as we go along. So first of all, well, what is the Ampere-Maxwell law? And we got this far at the end of last week. So the Ampere-Maxwell law is that the curl of B is mu naught J. And we studied this all through lectures 3, 4, 5 and 6. And we saw that then we proved, again, this is just a bit of revision, charge conservation can be expressed by this differential equation. So again, this should be in your notes from last time, but I'll just pop it up on this side so that we've got this beautiful concise differential equation for charge conservation. And Maxwell took the divergence of this equation, and the divergence of the curl was always equal to 0. And if you take the divergence of J on this side of the equation, you get, of course, minus d rho by dt. And as I said, you've only got to move a bit of charge around, and that's non-zero. So there was clearly a contradiction between charge conservation and this equation. Incidentally, I got asked a very interesting question at the end, and Maxwell, I did the lecture in what I think is like a more modern logical way, where I said this is the equation of charge conservation, and then I applied it to the Ampere-Maxwell derivation. Maxwell historically took the divergence of this equation and asked himself, what is del dot J? And the question I was asked, well, why did Maxwell take the divergence of the Ampere's law? And the answer is, he was a genius. He just saw it was the right thing to do. I think, you know, we can't sort of like answer a question like that. But what he did see was that we had to add this term to the right-hand side of the equation. And now when we take the divergence, remember I can take the divergence of dE by dt is the same as dE by dt of the divergence. We know from Maxwell's first law that the divergence of E is rho over epsilon naught. So when I take the divergence of this term, I get a rho over epsilon naught. The epsilon naughts cancel, and I've got a plus mu naught d rho by dt. And here I've got a minus mu naught d rho by dt. And that's the whole point, is that this equation now automatically fulfills charge conservation. So we had this towards the end of the last lecture, but let's make it 10.1, and the corresponding integral form, let's have this on the, again, we'll keep this on the side here. The corresponding integral form is that the line integral of BDS around any closed loop gamma is equal to the surface mu naught times the surface integral of the current density through the loop plus mu naught epsilon naught times the surface integral of dE by dt over the area bounded by the loop. So, of course, if we knock this term off, we've just got back to the Ampere law, and we've seen that this term is necessary for the charge conservation. So I'll make that equation 10.2. This is the corresponding integral form. And again, I'm not, we're not in here to do, history lessons, but again, it was interesting that historically what happened was all the phenomena of electricity and magnetism got written down as integral equations, and Maxwell abstracted the differential equations from them. Now, the Ampere-Maxwell law was actually discovered as a differential equation, but of course we can go the other way with Stokes' theorem and turn that differential equation into an integral equation. And then the surface integral on the right-hand side just becomes the surface integral of this term plus the surface integral of this term. And again, remember, I can take this derivative inside or outside the integral sign. So the whole theme of this lecture will be, how does this new term work? It's amazing, like for a century, the experimentalists have been in the lead, and they've made like Faraday, Ampere, going right back, Gauss, Coulomb, over a century have made these amazing discoveries, and the theoreticians have been trying to catch up. And now the theoreticians, in particular, one of the greatest of them all, take the lead, and we've got an entirely new term to deal with, and of course it's got massive physical consequences, and we're going to look at two of those today. The first of which is this magnetic field near a charging capacitor, which is illustrated in figure 46 of the course handout. So the idea is that we've got a current here which is flowing down towards some capacitor plates, and if this is conventional current, a positive charge will be piling up on this plate, and then the current, somewhere out here, we've got a battery, as part of a circuit, but being a physicist circuit, of course, these wires are infinitely long, and the current flows off this plate, and so if it's conventional current, a negative charge is piling up on this plate. Now, in the region in between the capacitor plates, let's say we've got a vacuum, because that makes it conceptually really clear that we have got a vacuum. So the problem with this is, well, we've already done this by Ampere's law. Here's a loop of radius r, and we know that there's a magnetic field B circulating around the wire, and we already did the derivation that the magnitude of B is equal to mu naught over 2 pi I over r, and that we actually did that in two ways. We did it semi-intuitively with Ampere's law, and we did it more kind of rigorously with the vector potential. We certainly know that that's true. So let's say now that this is, for example, the x direction going down here. We can choose our axes as we like. So I'm going to do two examples. Example one is the magnetic field near a charging capacitor. And we appear to have a problem. If the current is flowing down the x-axis, this is just to give it a label. You know, we could have chosen, made it the y-axis, we could have made it the z-axis, that's not important. But just to give it a label, if it's flowing down the z-axis, then Ampere's law applied to the loops gamma 1 is the loop upper loop, and gamma 2 seem to give us, it's only seem, we're going to correct things up in a minute, seem to give us that the magnetic field strength plotted as a function of x is constant here, but then suddenly drops to 0 when we get between the capacitor plates, and then suddenly goes back up again. Because what's happening here is that there's no current flowing between these plates. There's a vacuum in between, yeah? So if you see, I apply Ampere's law. The current flowing down here doesn't, you know, it's in an infinitely long wire. It doesn't know it's heading for a capacitor plate. It's just a current. You know, the electrons are flowing, or positive conventional current is flowing in some distant circuit. And if I apply Ampere's law here to this loop gamma 1, which is the flat surface bounded by this loop, you see in this, the surface S1, again, you need a bit of 3D imagination. Let's say, this is the bit where I can't open my give this to someone in the front row to open while I tat around for a bit. This is a, oh, thank you, Michael, gosh. Oh, a strong man in the front row, thank you. So imagine that this is the flat surface. The current is going down and the capacitor plate sort of over here. If I take my loop gamma in a bit where the real wire is, I would seem, by applying Ampere's law, to get this non-zero mu naught times I over 2 pi r field. And let's just represent it by this constant value. But now, remember, the loop gamma 2, if you like, you know, thinking that this is sort of drawn vertically, the loop gamma 2 is again a circle, but now the plane, the flat plane of this, goes in between the capacitor plates. And there's absolutely no current flowing through that. There's no current whatsoever in that region. It's a vacuum. There are no charged particles passing through that surface whatsoever. So just by Ampere's law alone, well, if there's no current, there's no magnetic field. So suddenly the magnetic field drops to 0. And then I get to the other capacitor plate. It's not drawn on, but you know, it's the same argument. Of course, I could put a loop around here and apply the argument to some surface S3. Well, now again, I've got a real current I flowing through here. So it goes back up, and because those two currents are equal, it seems to come back up to a finite value. Now you may think, well, you know, how likely is this magnetic field to be on a scale of 1 to 10? You know, it's not only is it not very likely, but I can do the experiment with a Hall probe. And so the answer is it doesn't. However, things are actually even worse. You might think, oh, you know, we've got all these clever theoretical arguments and he's now relying on some kind of like empirical fact. That gets even worse if you consider the surface here, S1 prime, which is a bowl-shaped surface. It's still bounded by the loop gamma 1, but now I construct it. Remember, it's an imaginary surface. It's a Stokes surface. I imagine a bowl-shaped surface which is still bounded by the loop gamma. And thanks to the efforts in the front row there, I've now got a bowl-shaped surface as well as a flat surface. So imagine now that the current is flowing along. Yeah, this you see, Stokes theorem. This was a point I mentioned early in the course. Is Stokes theorem applies to any surface bounded by the loop gamma. Well, give or take a tiny bit, and these are actually the same. This is the same loop gamma as this loop here. Yeah. So the flux through any surface bounded by this loop, it's not just the flat surface bounded by the loop. Remember, Stokes theorem will apply. I can always make this surface locally flat at any point. Now you see the current is flowing into here, and I make my surface, but I make the bowl so that the curved part goes round in between the capacitor plates. Yeah. So the bowl goes round in between the capacitor plates here, and there's no current flowing through the bowl-shaped surface at all because the capacitor plate stops here. Yeah? So there's actually, through the bowl surface, there's no current whatsoever going through this S1. And now the argument gets even worse than what we thought there, because this loop gamma 1, well, I've already analysed it. I know the answer by putting the flat surface S1 into that loop gamma. I now put this bowl-shaped surface in, and there's no current flowing through it. The current has stopped here. It's not flowing through at any point. There's no current flowing through the bowl-shaped surface. So when I analyse with S1 prime, I get that the magnitude of the field is naught. So I've analysed the same loop gamma and got two completely different answers. And so this is a disaster. So let's not pretend otherwise. It is a disaster. Let's say that. So the situation is even worse if we analyse the loop gamma 1 bounded by S1 and by the bowl-shaped surface S1 prime. There's the same loop, but instead of filling in with a flat surface, we take a bowl that goes around in between the capacitor plates using S1, which we've already done loads of times. We get the magnitude of the field is mu naught I over 2 pi r, and using S1 prime, the magnitude of the magnetic field is naught, because there's no current going through it. So we've applied Stokes theorem, and we've got two completely different answers for two different surfaces bounded by the same curve. So, we're in trouble. Well, we know Ampere's law isn't true. We haven't yet considered what this term contributes. And of course, although there's no current between the capacitor plates, there is quite definitely a changing electric field. And again, I'll sketch the argument sort of on the view graph here. Well, we know there's an electric field between capacitor plates, and we know the field lines point from positive to negative, and with our usual approximation we're not going to worry about some tricky little edge effects. We're going to pretend that the field is absolutely uniform across the capacitor. So using Gauss's, we haven't done much electrostatics in this course, but as I said, you've done a lot of the electrostatics last year. So using Gauss's flux law of electrostatics, the electric field between the capacitor plates is given by magnitude of the electric field between two infinite flat plates is you could express it, well, the electric field as the voltage divided by the distance. In terms of the surface charge density on the plates, everyone totally fluent in EM1 electrostatics, it's equal to sigma over epsilon naught. Again, you can revise that in from your notes from EM1 last year, or from a book like Young and Friedman. Straightforward application of Gauss's flux law of electrostatics, where sigma is the surface charge density, and this is in coulombs per square metre between the plates. So we get a non-zero electric field between the plates. So this is, oops, let's get that going the other way, move this up a bit. So this integral of E dot n dA over this surface, let's take it first of all through S2, or it could be S1 prime. Well, this is just equal to, and again we've got an, this is why it's set up as a particularly simple problem. Of course, if we just take this loop gamma 2, which is, this is representing into, of course, and out of the page, this loop, and we filled in with a flat surface, clearly the field lines E dot n, well, the surface normal to this surface is in the same direction. Our usual thing, this is just the magnitude of E. So if I integrate over the area, then I'm just integrating this over the area, but inside a parallel plate capacitor, this is just constant, so it comes out the integral sign. So this whole thing is just E times the area of the plates. And that's, again, we've used this argument so often. This surface integral is just E times the area of the plates. Yeah. So this integral is equal to, again, I should strictly speaking write it in this way, E times A, but this is equal to, we know in between the plates it's sigma over epsilon naught, so this is sigma A over epsilon naught. So we've got now this electric field between the capacitor plates when we, and because it's constant and because these two vectors are always parallel, it's just the magnitude of E. But by Gauss's flux law of electrostatics, that's sigma A over E, but that's just equal to, this is the surface density in charge per square coulomb, coulomb per square metre. I should say that again. So this is just equal to Q over epsilon naught, where Q is the total charge on the plate. So this whole second term here is just mu naught epsilon naught times d by dt of q. So this is, we're now getting very close. You probably even see the answer emerging now. So the second term on the right hand side of the Ampere-Maxwell law, just abbreviate, the whole lecture's about the Ampere-Maxwell law, is mu naught epsilon naught d by dt of q over epsilon naught. Mu naught epsilon naught d by dt of q over epsilon naught. Yeah, of course the epsilon naughts cancel, so it's just equal to mu naught dq by dt. And again, we now get to the stage where we're effectively applying charge conservation. This current I that's flowing down the wire is the number of coulombs per second which is arriving on the plate. So the rate of change of charge on this plate due to the current is almost by definition I is dq by dt. Is precisely what it's got this current I flowing down the wire, it's depositing q coulombs per second, and the extra charge accumulating on the plate per second is exactly dq by dt. So, but let's just use this corner of the board so I can complete the calculation here. But if you like, by conservation of charge, that current is all piling up on the plate. By conservation of charge, I is dq by dt. Therefore, the right hand side is mu naught I, as before. So in the region between the capacitor plates, there's no real current flowing at all, but there is a dq, there is a dE by dt, because the electric field is increasing as a function of time as the charge piles up onto the capacitor plates. There's a dE by dt term here, which when we work it out and put it into the law of the second part, this term, although it doesn't look like it's going to give us mu naught I, this precisely gives us the exactly correct field between the plates. So in region, if you look at it back again to the diagram, up here, again, it's a typical physicist's example. I mean, in general, both the terms in the Ampere-Maxwell law can be non-zero. Yeah? They don't have to be all one or all the other. Because we want to bring out the principles of the physics, we do it in this way. And in this region, this wire's got no charge on it. The charge carriers are drifting past the iron cores, usually electrons drifting past, say, copper Cu plus iron cores. So there's no electric field around in this part because this wire's not charged. There's no electric field here, and where there's no electric field, there's no dE by dt. So if I analyse in this part, somewhere up here in this part of the wire, I have just a current and no dE by dt, and that's what gives me this result. If I analyse in this region here between the capacitor plates, there's no real current, but there's a dE by dt, and that precisely ends up by giving me the same right hand side, because this is just the straightforward application. We can calculate the field, it's q over epsilon naught, the epsilon naughts cancel, and we just get mu naught dq by dt. And almost by definition, dq by dt is the current in the wire. So the Ampere-Maxwell law gives us, come back to our first worry about this problem, that's what we got by just analysing the first term on the right hand side of the Ampere-Maxwell law. In this region, there's no contribution from current, but we get a dE by dt term, which gives us this, and that gives us precisely the correct field, which we can measure experimentally. So this term is, you see, it's not like just some weirdo, you know, like charge conservation, and then we're going to go on to use it to, you know, derive the relationship between mu naught epsilon naught and the speed of light. We need it even in these very humble circumstances in which we charge up a capacitor. If we analyse that problem just from Ampere's law, we get the wrong answer. This was a case where in this region here, we got a magnetic field even though there was no current. I'm now going to go, and so between the capacitor plates, we do get a magnetic field purely because there's a dE by dt. So I'm now going to another, of course, physicist example, extreme example, where we get a current but no magnetic field. And back to our friendly radioactive tennis ball from lecture 9. And again, why I said right at the beginning to use the idea of this current density vector rather than scalar currents is we can now analyse, for example, a spherical current. And if I've got beta particles or alpha particles shooting out of this radioactive tennis ball, well, it's bad news for the front row, it's bad news for me, but from a physics point of view, it presents us with this nice spherical current. So, I mean, we've definitely got a current flowing out of there. You know, we've got charged particles, loads of them, spraying out of this ball. That is a current in space. There's definitely quite a few coulombs, or microcoulombs, whatever it is, flowing per square centimetre per second through each element of this, and so we've clearly got a current in this case. However, have we got a magnetic field? Even from the outset, well, our kind of intuition tells us this can't be right. What's the magnetic field circulating around? A sphere has got spherical symmetry. It's only when you give a lecture that you can say rubbish like that. I said, hey, our lecturer told us the sphere's got spherical symmetry. Obviously, it's got spherical symmetry. So what could this rotate around? Is it kind of, the magnetic field going around the North Pole, or is it sort of circulating around the equator, or some weird angle in between? And your kind of intuition is that for each bit of current, there'll be a circulation in this sense, and 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 somehow they should all cancel each other out. And even if you've not done, some difficult topology course in the maths department, your intuition might tell you the magnetic field would be zero, and if you're an experimentalist, you get your Hall meter and wave it around everywhere around, and you don't measure a thing. There's absolutely no magnetic field, even though there's a definite current. And again, this is where Ampere's law gives us the wrong answer, and the Ampere-Maxwell law gives us the right answer. This time, because I used, if you like, the integral form last time, I'm going to use the differential form this time. And in particular, I'm going to, again, like I did last time, because I think it just makes it easier, makes it clearer, I'm going to divide through by this scalar. So it's like the opposite problem. If we analyse a spherical current, we don't usually think of currents spreading out in a sphere, but we certainly can easily set it up. A spherical ball of radioactive material would do the job for us. If we analyse a spherical current, and this is illustrated in figure 47 of the course handout, we have a non-zero J. Obviously, we've got a current, but it appears that the magnetic field is naught. And again, this seems to be a bit of a conundrum just from Ampere's law. So how does the Ampere-Maxwell law help us out on this occasion? Well, being as I decided to redo this in terms of the spherical current at the last minute in terms of the differential law, I'll just check this out. So basically now we've got, by charge conservation, we have got that dq enclosed, this is the charge enclosed by the sphere, is equal to minus 4 pi r squared J of r, where this J of r is to emphasise it's a radial current. And if you like here, again, last time, when we did charge conservation, we had that again, we got to get used to using differential and integral forms of all the equations. Some of them are easier to apply in some circumstances. Of course, if I integrate the current density's normal component over the surface, I must get the negative rate of decrease of charge enclosed by the sphere. And again, here, because it's radial, the radial unit vector and J are always parallel to each other, and because of the spherical symmetry, the area, the magnitude of J comes outside the integral, and the integral just becomes the integral over the surface of a sphere, which is 4 pi r squared. So this is just saying, what's charge conservation in this problem? Now, again, possibly, just to make this a little bit clearer, or let's rearrange it. Our current density, J of r, is equal to minus 1 over 4 pi r squared dq by dt. And again, this is what I mean by having some kind of conceptual problem, is that this is clearly a this is the current density is clearly non-zero in this case. But now, again, we know the electric field of a sphere. And if you don't know this, you are in deep trouble on the course, because this is, again, very elementary, goes right back, if you like, even to Coulomb's law, let alone the Gauss flux law of electrostatics, that the electric field of a ball of charge is the charge inside over 4 pi epsilon naught r squared. And as you know, if I put a test charge, say that was Q1, and I put a test charge Q2 into this field, again, I'm using this as an abbreviation, excuse me, for the modulus of E. Let's just leave it like that. It's a spherically symmetric problem. I've got that there's an electric field here of magnitude Q over 4 pi epsilon naught r squared. So if that was Q1 and I put Q2 in it, I get the magnitude of the Coulomb force between the charge that I bring into the test field. So now you see again how the calculation's developing. I've got two terms here. I've got a real current, but I've also got an electric field that's changing with time, because the Q is emphatically changing with time. As the charges go out, there's a dq by dt. So therefore, dE by dt, well, we're not changing the radius of the sphere, are we? We're changing the charge inside it. So the r comes out front. It's 1 over 4 pi epsilon naught r squared dq by dt. Therefore, epsilon naught dE by dt is equal to 1 over 4 pi r squared dq by dt. So we're outside this sphere. We've got a non-zero current density, which is spreading out over space, but we've also got a non-zero dE by dt term. And this term here, epsilon naught dE by dt, and this term here are precisely equal and opposite. Minus 1 over 4 pi r squared dq by dt plus 1, when I've multiplied by epsilon naught, plus 1 over 4 pi r squared dq by dt. So when I go back to analyse in terms of this equation. I mean, it's written as a vector equation, but here you can see that this term, the J of R and the epsilon naught dE by dt are exactly equal and opposite, and that doesn't depend on what radius I've chosen. So these two terms cancel. So again, the Ampere-Maxwell law in this circumstance, I mean, that's definitely not zero. It's minus 1 over 4 pi r squared dq by dt. That's definitely not zero, but it's plus 1 over 4 pi r squared dq by dt. So the right-hand side of the law gives us nothing, and therefore we've got no curl. We know also that the magnetic field has also got no divergence, and a field that's got no divergence and no curl at any distance r from the centre is zero. So we have proved, therefore, that with the Ampere-Maxwell law, we've solved that problem. There's no topological problem about what B is circulating around. There is no B field in this case. So again, let's just tidy that up with a last board note. So the two terms on the right-hand side of the Ampere-Maxwell law are therefore equal and opposite in this case. So curl of B is zero. We already know, because it's totally fundamental law, that del dot B is zero. Nobody's ever discovered a magnetic monopole. So at any R, B is zero. A spherical current produces no magnetic field. And this is experimentally true as well. So that's really as far as I want to go with the Ampere-Maxwell law before we use it tomorrow. Sorry, on Wednesday in the unification theory. We're actually not proceeded historically. Maxwell, as soon as he discovered the new term, went straight on to the speed of light calculation. But I want to, because some people think, oh, that term's just been lobbed in for charge conservation, and it's just something to do with the unification theory. You can see these are two pretty prosaic cases. Just charging up a capacitor or analysing the magnetic field around a spherical current, you've got to have this term. This mu naught epsilon naught dE by dt term is vital to analyse even these straightforward basic circumstances. And so I've been trying to root, if you like, this term in a kind of physical reality, and you can see that it works. So just as a preamble for the lecture next time, which is certainly, I'm going to obviously be using Maxwell's electromagnetic theory, wave theory of light, all through our study on optics. So please keep in touch with the course at this, particularly this week's probably the most important. We started off with a little bit of electrostatics. And we saw that that's only a static approximation, and that Faraday's law could be written in this way. We then started off with a little bit of magnetostatics, where we got this equation, and we saw that kind of can give us the Biot-Savart law. And then we saw in the dynamic case that we've got plus mu naught epsilon naught dE by dt. So we're in full possession of all four Maxwell equations now. We've seen how these are really rooted in experimental reality. Now, it's often, as I've done it in a way that most people do, started off with the static approximation here and killed that term, and I've started off with the static approximation here and killed that term. In other words, the fields themselves were static. There was no dB by dt, no dE by dt. Now, there is a method of solving all four Maxwell equations at the same time. It's called the method of Leonard-Vickert potentials after its discoverers, and that is quite difficult mathematically. I want to emphasize, you can solve the Maxwell equations completely as a set, but you can imagine it's pretty difficult. If you've got charges and currents and dynamic magnetic fields, it's a tricky problem. So what we're going to do, and indeed we are following Maxwell, is we're going to take, if you like, the opposite approximations, the dynamic approximations. So we're going to make this equal to 0, and we're going to make this equal to 0. And that with the justification that if we're a long way away from any sources of charge or current, those terms are 0 just because they're so far away. You know, if there's a point charge over in the corner there, up at the back, you're not going to get much of an electric field from it. But certainly if I shake it, you will get the electromagnetic wave. That's the point. Likewise, I could have a little current, you know, flowing down this piece of chalk here. Well, up at the back there, you're not really going to experience the direct magnetic field, but you will appreciate an electromagnetic wave if I change this current. So these are called the, so we now have the full set of Maxwell equations. And indeed, this is where kind of Maxwell got. In 1861, his sort of genius, he'd abstracted the reality, he'd predicted this term, and you can solve them all simultaneously, but it's a very, very difficult piece of mathematics. We will now, as interpreted in Friday's study, what are called Maxwell's equations in free space. And free space, we've got 2 lectures on this. This means far away from any charges or currents where rho is 0 and J is 0. And that's how we're going to study the wave equation. And Maxwell's equations in free space are specifically that the divergence of the electric field is 0, the curl of the electric field is minus dB by dt, the divergence of the magnetic field is always 0, and del cross B, we've studied, of course, the approximation this way round. We're going to take it this way round, where the curl of the magnetic field is plus mu naught epsilon naught dE by dt. We've still got 5 minutes left, and in that time I'd just like, again, I mentioned this before last week, is to do a tiny bit of revision of wave equations, because I know it's quite a long time since you did waves. So if you want to get the most out of the unification theory, and I hope you do, you know, you've done all the hard work now. Actually, the unification theory is now relatively easy once you understand the differential equations. And you can imagine how we're going to go about it is that if I take, and why that curl of the curl is important, you know, as a vector identity, because you can see this is almost, because both fields in free space have got 0 divergence, but have got non-zero curls, I'm going to take the curl of this equation, yeah? And by the curl of this, as I've said several times in the last week, is d by dt of the curl of B. And because I've got the expression for the curl of B, I can eliminate B from the equation and get an equation that is just for the electric field. And I'm going, of course, to prove that it's a wave equation. So a kind of essential revision is, you know, like last year in Phil Lightfoot's Vibrations and Waves course, you studied mechanical waves. And although these are not emphatically mechanical waves, they're waves in a vacuum, something that to this day people find hard to imagine. And chapter 15 of the book that you all got last year talks about the mechanical waves, in particularly on page 530 of the edition I've got. You know, I'm sure you can find it if you've got a slightly different edition. This is a wave function where you've got some amplitude and you've got something that's periodic in space and periodic in time, where the angular frequency in space is 2 pi over the wavelength. You've used this a lot in solid state, and the angular frequency in time is 2 pi over the period. A wave equation in general for any function which of this type, and again, practice, if you know, before the next lecture, just plug that into there, show that it's right. d 2 psi by dx squared is 1 over v squared times d 2 psi by dt squared. So this is a wave equation where v is the velocity of the wave. Now, when you get a wave velocity, the example, and I think you did this with Phil, and it's in the Sears and Zemansky book, you get that the velocity is equal to the square root of the tension in the string divided by the mass per unit length. And the way that you get a wave velocity is you make some physical argument. So in this case, you've got this is transverse waves on a string. Imagine I've got a taut string stretched out to the kind of lectern there, and I flick this end. Well, then, of course, it's not that the string goes anywhere, but the displacement moves along at some finite velocity. In that case, you apply Newton's laws of motion to that situation, and when you apply Newton's laws of motion, you find, sorry, let's use a pen that actually shows up. When you apply Newton's laws of motion, a physics argument, you find, oh, d 2 psi by dx squared is equal to mu over the tension times d 2 psi by dt squared. In this case, this thing here comes from applying Newton's laws. You know, if I give something a flick and send a mechanical wave down it, well, of course it obeys Newton's laws of motion. And then, having got this equation from a physics argument, I say, oh, but wait a minute, that's a wave equation, and therefore 1 over v squared is mu over t. In other words, v squared is equal to t over mu, and v is equal to the square root of t over mu. So I'm going to use a very similar style of argument, which is I'm going to show that the electric field and the magnetic field satisfy an equation of this type, and then I'm going to identify the constant that I get from the electromagnetic interaction with 1 over v squared and derive the speed of the wave. So anyway, let's leave something to Wednesday, and yeah, as I say, do try and make a big effort. I know Wednesday's a 9 o'clock lecture in a not great lecture theatre, but it's the most important.